what I'd like to share with you is some work we've been doing on verifying strategic ability of multi-agent system, but as you will see, a new form of multi-agent system that we've introduced. And this has got some connections also with developments in machine learning, and for example, the invited talk by Gary Marcus that we heard a couple of days ago. So if I look at a multi-agent system, that's probably a picture you're familiar with. We have a collection of agents that are interacting with one another and interacting with the environment. And what I like to think about, if I'm thinking about the agent, is a stack of layers, of modules, starting from perception, going to reasoning and maybe action selection, decision making. If you're coming from engineering, you have control in mind, ultimately with an action that is performed on the environment, which together with the other agents, triggers the next state. Okay, and of course, we've seen some presentations today, and we've seen many papers over the years motivating and developing work in terms of establishing strategic properties of interactions. And why do we want to do that? Well, we want to study how different agents interact with one another so that we can predict particular states of affairs that may result, or more generally in a strategic setting, even equilibrium states that may actually result. Okay, and we know what model checking means here. We have a system and a logic specification. We want to establish whether or not the specification is met. Now, ATL, as we know, is widely used in a variety of contexts. It's been extended to other logics. It's been extended to ATL star. It's been extended to strategy logic. But at the core, alternating time, temporal logic, and before ATL, coordination logic, were kind of basic building blocks for us to talk about strategic abilities. Now, we know there's been a lot of work in extending this and a lot of tools trying to automate that process. And yet, what I'd like to point your attention to is that at the heart, what we're dealing with is a model of an agent which is symbolic. Okay, so if you were to dig deeper into your model, you will find things like concurrent gain structures. If you look at my papers, you'll be looking at interpreted systems. But ultimately, these are all symbolic representation, logic-based representations. Okay, you will find ultimately some sort of structure such as this. Well, as we know, things have been changing over recent years. In particular, what we know now is that perception is largely in robotics and autonomous vehicles and autonomous systems generally, is largely implemented these days through neural networks. So the question I'd like to begin to address is, how do we actually verify a system in which, for example, perception is not actually implemented in a logical setting, such as, for example, some approaches that Michael Woolridge and myself put forward 15 years ago called the BSK logics, but actually they are implemented by machine learning, in particular neural networks. So that is the background that I wanted to share with you. And let me summarize what we do in the paper. Inevitably, there is not enough time in this presentation to go through the details, but let me just highlight some of the key points. So what we do is that we introduce a new model of agents, which we call neural symbolic. Okay, so in our model, you have a perception layer, which is implemented by a neural network or a series of neural networks, like you will see in an example. And then you have a controller unit, which is symbolic. Okay, so and they live one together with the other. Okay, that could be implemented with an interpreted system, a concurrent gain structure, and so on. And together they live and perform actions on the environment, they synchronize, they do all the sort of things that we've been doing in this community for many years. Okay. Now, in previous KRs, a KR that we held in person, luckily in Tempe, a couple of years back, I presented a paper in which we were looking at reachability analysis of a system which only composed of neural networks. What we're doing now is that we are combining a symbolic controller unit with a neural-based perception unit, and we are trying to verify strategic interplay. That's the contribution of this paper. Okay, so just a little bit more in detail. Let me share with you one key definition here. That's the definition of a neurosymbolic agent. Okay, so it is actually very similar to what you're familiar with. Okay, so it starts with a set of states. How's that different from what you know? Well, these set of states are set of pairs that comprise private states and percepts. Now, private states are not going to be new to you. Percepts may be new to some of you, but these are also familiar in formally such as interpret systems. What is really different is that these, in general, are vectors from real numbers. Okay, that we don't say that we have a number of states and this is the states you have. These are vectors from real numbers. And you have an observation function, this obs-a, which actually implements the function that's implemented by a feed-forward neural network. And in particular, we're only working with piecewise linear networks. Okay, piecewise linear networks are very important in machine learning. For example, the ReLU function, which is widely used in perception, is a piecewise linear network. Okay, so your observation function is a function from vectors in real numbers, h and m is the dimension that you have, into R of n. Okay? Then you have a set of non-empty actions. You have a protocol which decides what action you're performing, and you have a transition function which is exactly the one that you expect, right? You start from a set of local states. You have a joint action for all the agents in the environment, and you make a transition into a new state. Okay. I could give you the definition for the environment. I could give you the definition for the strategies. You could build the system in that way. You could then perform all the possible executions that this system would create. I think you can imagine all of this because it's not very different from what you know already, and you find full details of this in the paper. We just move on instead with some of the key properties that you check. Now, we have a fragment of ATL star in which we have things such as xk. So we call this bounded fragment of ATL star. And the atoms that we use could be regarded as propositional atoms, but actually in the implementation that we have these equalities over the real numbers. Okay, so you will be able to write and in the tool, for example, if you use it, you'll be able to write these equalities over vectors of real numbers. For example, the intruder has a strategy to cause a near mid-air collision after k time steps. Is something that you would write in such a way. Okay, so what's the verification problem? Again, nothing new here. Establishing whether or not an ATL property is satisfied. Turns out that verifying these sort of systems, even against reachability, is undecidable. Okay, and that is why we introduce a variant of ATL in such a way. Now, how do we do verification? The way we do verification, and this is built from other work we've been doing in our group in verifying perception systems, and is compiled into mixed integer linear programming. Now, remember your lessons at school on optimization. A MIL problem is an optimization defined on a linear objective function to be maximized or minimized with respect to linear constraints, and it's mixed because it contains both real and binary variables. Okay. So in SAT, in SNT, we say routinely, now the tools are really great. You can build a query with lots of variables. You pass it on to an SNT solver. The same happens in optimization. You have now tools that solve queries of MIL problems with thousands of variables. And one of these tools is Groby. So what we do in the paper is that we present two different encodings into MIL problems. One that can be run sequentially, another one that can be run compositionally, and we provide implementation supporting both. So let me share with you the news regarding the complexity of verifying neurosymbolic agents against this bounded fragment. Well, so two results. Verifying these agents against bounded ACTL star is p-space hard. This follows from reducing QBF validity into a class of systems we studied before. As an upper bound, verifying neurosymbolic agents is in Kohn-Epstein complete, okay? And that follows from the fact that feasibility check of MIL can be done in polynomially in the size of the MIL program. And so all we have to explore is actually the size of the MIL programs that you generate. And that's something that we do in the paper. Just checking the time, I've got a couple of minutes left, I think. So let me not discuss the encodings with you. Again, details of this are in the paper, but let me just give you maybe just one, just a hint of an explanation as to the first line. So this is saying that this is a sound and complete encoding because the system verifying this bounded ATL specification is the case if and only if this problem whose definition you will find in the paper, it's a MILP problem that associates the specification that you're trying to check on the initial states is infeasible, that is, has no solution. That means that whenever you find a solution, you have the counterexample for the model checking problem that you're trying to establish. In other words, you find the particular instances that will realize that counterexample. Okay, so I was just saying in the paper we give both a monolithic encoding, we also give a compositional encoding, and we present a tool that you can download from our website that actually implements both of them. Right, as an example of all of this, we modeled, we modified this from Stanford, and at Stanford they're working on similar problems with aircraft collision avoidance systems. So these are realistic systems in which you get an advisory from your system that looks at how the system is performing and whether you have other airplanes in the surroundings, and gives an advisory to the pilot as to whether you should climb, keep the vertical altitude the same, or do whatever action. Okay, so the agents obtain advisories when perceiving the environment, and then the agents decide the acceleration based on the advisory. And this decision could be non-deterministic, okay? So the neural networks that we've been using are something like this. They have a number of layers, so they're deep networks. They have about 50 nodes in each of the layers. And ultimately, they provide advisories that could be descending 1,500 feet or ascend 1,500 feet. And then the pilot will actually try, will perform an action and act on these actions. So we use the tool to verify instances such as the on-chip has a strategy for the system to be in a safe configuration after case steps, or the intruder has no strategy.
1 minute.
I'm sorry, 1 minute you said.
Sorry for the,
you said
just go ahead, 1 moment.
Yeah, no, that's fine. And so let me share with you some of the numbers to show with you that not everything is rosy. This is the performance that we got out of the tool. You see that we struggled to verify properties after 5 or 6 steps. I have to say that the state space of actually one of these steps is very large, both because of the neural networks and because of the global state is very large. And of course, we're working on real numbers. So it gives you an idea of how many steps we could actually verify for such a large system. So let me wrap up. For quite some time, I don't think Gary was the first one to mention this the other day, there's been a push to work on hybrid models. The model we put forward here is a neural symbolic multi-agent system, following also papers in AI. I'm thinking of Atogasses, Luis Lamb, and others. This is good for identifying shallow bugs, like in bounded model checking. I don't think it would make sense to try and work with this to verify very long executions of the system. This is publicly available. Feel free to send us an email if you cannot get the tool to work. The bottleneck is efficiency, as I said, and what we're working on is to improve scalability. So we actually have a number of parallel lines in the group in optimizing the compilations that we're making into MILP. And of course, this is very much related to our side work that we have next to this, which is verifying perception systems against things such as robustness and so on. I think I'm going to stop here. Thank you.